Okay, I'm going to do example 4.04, but it's dropping a projectile from an airplane. But before I do that, I'm going to talk about what happens if we launch something from the ground and it returns back to the ground, or from some altitude h. It could be at the top of the building, but it lands at another building at the same altitude. Let's go ahead and say this cannonball gets shot out with some vector. We'll call it V0, and it's at some angle theta to the x-axis. The path is going to look something like this. Assume that there's no drag. And all of these tips right now are only if it launches from the same spot that it lands. So pretend that it launched from the origin at 0, 0. The first thing we should do whenever we see this is break it up into x and y components, because we only have gravity acting in one direction. Gravity is acting downwards the whole time. And it always acts at the same magnitude, negative 9.81. And that is our acceleration. It's our constant acceleration. But in the x direction, we don't have an acceleration. So for our x direction, we will get V0 cosine theta. And you can, if it was pointing this way, still use that angle. So it could be an angle bigger than 90, and it'll give you the direction or the plus or minus sign for you. I recommend it. And we get this component v sub y, the velocity in the y direction, as V0 sine theta. Alright, we have to do that because we have to analyze motion separately, like I said, because the velocity is going to remain constant in the x direction. So this blue vector, it's going to stay the same length. And that's because there's no drag, nothing's slowing it down. But we have Earth down here pulling us with a constant value of negative 9.81. So, I just wanted to show you some tips on how to get some basic stuff from this. Like, what if I wanted to find the max height, or the time to the top, or the total flight time? So let's start with time to the top. Time to the top, I would say use this kinematic equation. V final is equal to V0 plus the acceleration, which is the acceleration due to gravity, times time. We need to know that at the top right here, the velocity in the y direction is 0. So we say V final is 0. Now I get a negative V0 when I rearrange it is equal to g over t. And t is equal to negative V0 over g. And when we have to plug in this y component right here, we get a negative V0 sine theta over g. And when you plug in, put in minus sign in for g, it all works out. You don't have to, the minus signs will end up canceling on there. So that's how long it takes to get to the top right there. Then it's going to turn around and come back the other direction in the y direction. And to get how long it takes to where it lands, we would take that's called the flight time, the total time in air. We would take this number and multiply it by 2. So the total t, flight, let's call it t total, and this would be t 1/2. The total flight time would be equal to just 2 times V0 sine theta over the acceleration due to gravity. And then another thing, we could find, now that we know how long it took to get to the top, we could use either x final is equal to, or sorry, y final is equal to y0 plus the velocity in the y direction times time plus 1/2 gt squared. and figure out what this is. This goes to 0. We would have to put in v0 sine theta for the y component of the velocity, and we would plug in time that we just found, and we know what g is. Well, if we were just asked for the time to the max height, we didn't want to find the time to the top, we can jump straight to that. Because what you did basically was put this equation into this equation. Well, that's what this equation actually is. Okay, so, when you eliminate t from this equation 1 and this equation 2, you get this equation right here. And once again, when it gets to the top, the velocity is going to go to 0. And we can pull this over, get a negative v0 squared is equal to 2g delta y. And I can say delta y is equal to negative v0 squared over 2g, and the g would be negative again, so we can get v0 squared over 2g. What we need to remember though is delta y right here is y final minus y initial, or y naught. So in this case we started at the origin, we can cross it out. Sometimes you might be starting at a different altitude and then landing back at a different altitude, or that same altitude in this case, but that could be 50, right? So if we were on a building that was 50 meters tall, shot something over to the other side, or maybe a lake over to the other side where it was also 50 meters tall, we would put a 50 right there for our y naught. Otherwise, all we find is the displacement. And since we started at the origin, the displacement is equal to its final position. Okay, those are my tips for working with something that lands at the same altitude that it was launched from. Now let's look at example problem 4.04. A rescue plane flies at 198 kilometers per hour, and it is flying at a constant height. In other words, it's not going up or down. And it is going over a victim, and they need to drop a capsule right on top of them, apparently. Same thing if we had a bomber and the navigator had to find the angle of when to drop it. Typically that's done by holding the speed and knowing the altitude. My grandpa's a navigator, that's all. But what they want to know is what angle phi over here does it need to be released at to hit the victim. So what angle phi? They give us that the height is equal to 500 meters. They don't tell us anything about this distance, but they tell us that the plane is moving with a constant velocity. That velocity is in the the x direction only, and it is equal to 55.0 meters per second. They worked it out for us. So if this line right here represents the trajectory of the object in free fall, so we're still talking about free fall. This is only under the influence of gravity. Nothing else is touching it. There's no drag. There's no other forces. Just the force due to gravity. And this line right here is what they call the line of sight. So it's just a perfect line. That's not the line that the object is going to fall on. It's going to take this parabolic path right here. Okay, so what angle phi? How can we figure that out? First of all, what is this angle? Well, we use tangent inverse of an angle as the opposite over the adjacent, but we're usually given like this angle down here. Well, if this is opposite to this angle phi, and this is the adjacent, then in that case we have tangent inverse of phi equal to the x, we could call this x, right? The distance, delta x. over, we know the adjacent side, and it is 500. So we can get x is equal to, we'll just leave it right there for now. We'll come back. And the first thing I would do actually on this problem is figure out the time to drop. How long is it going to take to hit? In that case, just like, no, not like the last problem actually. I would use y final minus y naught is equal to the velocity in the y direction times time plus 1/2 times gt squared. Alright, the velocity in the y direction, 0. There was no up or down motion, so we get to cross that out. And we know what this is right here. This is the displacement delta y. That's equal to 500 meters. So we end up with 500 is equal to 1/2. We know this is a negative 9.81 meters per second squared. And we can solve for t. T ends up coming out to 10.1 seconds. That's how long it takes to hit the ground. With that, we could find out how far it goes right away. So, if we use the formula x final minus x naught is equal to the initial velocity in the x direction times time plus 1/2 acceleration in the x direction times time squared. Well, there is no acceleration in the x. We get to cancel that. The only thing acting on it is gravity, and that's acting in the y direction. Vx is equal to the, was it 55 meters per second? So we know that. And this would be equal to our delta x, or our total displacement, because we started at the origin. So it's x, this is actually the same, the displacement is equal to its position in this case. We know 55 meters per second, and we know the time. Oh, sorry, we don't know. Yes, we do. We just solved for 10.1 seconds. So we get an x final, or a total delta x, equal to 555.5 meters. That's how far it went. Whoa. Okay, and then what angle would we need? Well, if we go back to that tangent, let me see if I can just copy and paste it. The tangent inverse of that angle being equal to x over 500, we have x now. So we get phi as equal to the tangent inverse of 555.5 meters over 500 meters. And that ends up being an angle of 48 degrees. The last thing we could do is figure out what the velocity it hit the ground with. So it came down like this. And it's going to have some different velocity vector because the velocity vector in the y direction is going to be longer. The x component is still going to be equal to the 55 meters per second, but we have a new y component of velocity. So the velocity final in the y direction would be equal to the velocity initial in the y direction plus gravity times time. It was only going horizontal, so it has no velocity in the y direction. And we can say that it is equal to just the negative 9.81 meters per second times 10.1 seconds that it was in the air. So we get a negative 99.0 meters per second. So it was at rest, now it's not. And we can resolve this vector. This is the final velocity vector. We have a negative 99. We have a 55. We could figure out this angle right here, and we could figure out the magnitude, right? The magnitude would be equal to the square root of 99 squared plus 55 squared. We end up getting a 113 meters per second, and the angle that it hits would be equal to the tangent inverse of the opposite over the adjacent, and that's going to be equal to that's 60. So when we calculate it, we get 60.9 degrees, but this angle, if measured from the x-axis, I would say would be equal to 180 minus 60.9. Ta-da! Alright, and I guess we should put this back in vector form. The final velocity vector would be equal to some 55 meters per second in the I direction plus some negative 99 meters per second in the j direction.